Okay, so this is your second recording in chapter 8. We're going to start really the actual floor system where you have the T-beams and the slab together. Okay. Some of the things, we have already talked about it, but so are going to be reviewed, but other things are going to be new. So T-beams are basically the case when you pour your slab and your beams at the same time. Okay. And this is common in some buildings and bridges. Yeah? The figure we have is this one right here. Again, you have the beams here, right? You got the beams and the beams, right? And then the frames in this direction. And so you can see here the slab is all cast in place. So this is going to become a T-beam, right? For the purpose of designing, right? So that's what this model is, right? So this beam right here will be the H beam here, right? This portion right here is the length here. This beam right here is this beam, okay? And then the cantilever portion of the beam, which is that. Okay? So that's what we're looking at. Okay? So the important thing to remember here is that, of course, you're going to have here a little bit of a negative moment, right? And then you go into a positive moment, and then again you start having a negative moment, and this being cantilever most likely a negative moment, right? In terms of your shape, don't forget that these changes where you have zero moment are your points of inflection. So you got a curvature going this, and then it changes curvature, and then it changes back again. Okay? So that gives you a possible deflection shape. It's not the exact value, but at least you have an idea of what it may be. Okay? And so that's what we're showing on that figure, right? And there. So the other thing that we have to look at these, right, is that as we go here, right, on this portion, your reinforcing will be on the bottom part. Right here, you will have reinforcing on the top, and between E and C, you also have reinforcing on the top, right? That's your main reinforcing. You always have both because of the cage. But your main reinforcing still will be from D to E, will be positive. And of course, you will never stop at D or E. I mean, you have to take it a little past those points. Okay? In there. So one case then is AD and EBC, which is where you have your negative, right? So this portion right here and that one. So negative reinforcement. That is the case where you're going to put your tension bars on the top. And in this case, the code allows you to spread the bars along B sub F. A lot of designers try to concentrate this in the middle because of other construction issues. Like you had to make a hole in your slab and then you don't have to perforate through your main bars. Some people may put just half of the total load and the rest may be spread through the edges of the flange. So there are different options depending on what you want to achieve in your design. But the important thing is that this case, with a negative moment, right, your compression is at the bottom. So your compression is a rectangle, always, with a B equal to BW, the width of the web, right? And so that means that here you can use your regular formulas for design. This is not really a T-beam formula. Okay? When you go into the DE section, right? DE section, the positive, that's when we get into a little bit of a trouble, right? Because now the tension is at the bottom and the compression is at the top. And this is where we have those two cases, right? Where the A value could be within the flange. And that means we use the same formulas that we've been using, but with a B sub F as the width for the compression side, right? Or we may have to use the T section formula because the A value goes into the web, right? So that's something that we have seen already on these formulas that we already developed, right? So we have that, and that's what we're explaining on all this here. The HF here is what ACI calls the thickness of the flange. Some people call it T, right? T for thickness. But in ACI we call it HF, so height of the flange, width of the flange, height of the beam, which goes all the way to the top, right? And then your D value to the centroid of your bars, right? So D sub T, all that remains the same. Let's see, what else I'm missing here? No. Now there are the case of isolated T-beams. Those are more typical of precast construction, so we're not going to talk much about them, right? But that's another type of T-beam. So effective flange width. So remember, we haven't done that. Remember in the previous problems that we did, I gave you the formula. You have already the B sub F given. So what we're going to do here is to come out, or show you actually, the formulas for effective flange width. And why do we need to do that? Is because of this, right? The actual stress distribution is non-uniform, like this. Okay? And this is called the shear lag effect. So because this is wide, the forces are transferring little by little, and they are not completely uniform. So what we do then is say, okay, well, this is the 0.85 F prime C. Now I'm going to find, right, an equivalent width, right? This is your effective flange width, right? That will give me the same force, the equivalent force that I got in this case in here. But I will now have a nice rectangular shape rather than this shape, okay? So that's the purpose of the effective flange width. Okay? You're going to change a non-uniform distribution of stresses into a uniform distribution, equivalent uniform distribution of stresses. Okay. Mm-hmm. All right. So what do we have then in terms of notations? We have this. Okay. There is a flange width. There is the thickness of the slab, HF. There is the spacing between, the clear spacing between the beams. There is the width of the beam. There is the center to center length of the span length of the slab. And then there is the span length of the beams. Okay. So these are clear spacing, so face to face. So that's important to know. LN is also clear spacing. L slab is center to center. Now this one I already told you that in general this is a bad shape because it can torque, right? And as it torques, I mean, then you twist the section, and your loads are not coming directly now in the vertical plane. But because of the slab, that will be prevented, and so it works like a regular T-beam, even though it's an H-beam or perimeter beam or spandrel beam, right? So this is a perimeter beam, a spandrel beam, H-beam, right? Okay, so what are the formulas then? The code gives you the values for the shaded areas. So the code says in section 6321 that your overhanging portions should be the least of 8 HF, SW2, and L sub n over 8. So you have three choices. You pick the least value of these ones. Okay, so the smallest, right? And the same for the case of the spandrel beam. Okay. That's what it is in your ACI in section 6321, right? 6321. So if we go to your code, right, section 6321, right, so we have right here 6321. What am I doing? Okay. So TB in geometry, this is the one it give you. Okay. And so these are the same values that are just copy. Okay. But remember, it's for the overhanging flange. Okay. So this is not the total B sub f. This is just the overhanging flange of these. What am I looking for? I'm looking for the zoom. The search view. Zoom. Okay. All right. All right. So that's where we have this, and let me do that here. Right. Oops. This is different than that. So I need to go. Oops. Stop doing that. So where is my, I lost now my code. Oh, there it is. Oh, this is the one I was looking for. All right, but something I did wrong. All right, I don't know what I did wrong right here. All right. So this is the table, okay? So overhanging, that's all it is, okay? The overhanging portion, and that's what I said, that it only refers to the portion that is being shaded here, okay? What you want really is the total value, and so this is what then gives you the total value. So B sub f will be, of course, BW, right, plus ln over 8 on this side and ln over 8 on this side. So if both sides are equal, right, then you can do ln over 4. Now, if both sides are not equal, then you have an ln 1 over 4. And then, I mean, with the lengths are not equal, which is strange, right? Because this will be your beam, right? And so that would be a little different, all right? So unless you have beams that are not the same length, and then you have that problem. But other than that, this will be the same, so you can do then ln over 4. So ln is the clear span of the beam, okay, of the beam. Then here you have 8HF on this side, 8HF on the other side. And again, I mean, unless you change the sizes of your slabs, which could happen, I mean, not very common, but it can happen. Normally you would have BW plus 16HF. And the other one, which is this one, is your spacing divided by 2 and spacing divided by 2 here. So that means you're really looking at the center to center spacing between your elements. And so it will be BW plus SW. Okay. So that gives you center to center spacing of beams. And the same for the overhang. Okay, you can add that. You will add only one side, and then you get that. Right? Notice that your beam flange, right, cannot exceed. I mean, you cannot go past half of your clear spacing. I mean, that would be the maximum that you can use, right? You cannot go past that. So these are normally the formulas that we are going to use. And some of these, I don't know if all of them, but some are in your design aids. And I don't know if I didn't open your design aids this time. Oh, that's weird. Okay, so didn't open design aids. So let me see here. Design aids. So design aids. Where did my design? Where are my design aids? Huh. Oh, that's where the problem is. I have to go here. Okay, there, spring 20. Right. Okay, so here we have, right? And here are the values given for your T-beam. So notice that these values are here. These are the three values that I'm showing you here. Okay. So these are the two values. Okay. Oops, no, that's not what I want. So be careful because here, for example, this is in your FE exam formulas. It says span length because that's what it used to be, but now it's the clear span length. Okay, so this is now the clear span length. Okay? And here are the other formulas for the exterior one. And again, these now should read clear span length in here. Okay, so both of these now, instead of in the span length, but usually span length is center to center, these are now clear span lengths. All right, so now that we have those taken care of, that's where you find them. So you have in your design aids, you have it in your ACI. Okay? And then you have isolated T sections, like I said, precast members. Your B sub F has to be less or equal than 4 times your BW, and your thickness has to be greater or equal than 1.5 BW to have a geometry that usually works fine. Okay? Okay, so we already had the design formulas. We have developed those before. Remember, this is the case when the A value is in the flange, so we use that formula, but the B has to be your B sub F, right? And then there is your B sub F. When you go to your A is minimum, you check for these formulas here, right? A is minimum, and these are the same formulas we've been using. If your A goes into the flange, then we have this issue of having two different compression forces, and they have to be in equilibrium, and we developed this formula already. Your A value is this one, right? Your formula for moments is this one, that when you substitute numbers, it changes to this, right? And you have your A is minimum. Again, I mean, these formulas are given in your design aids. So you have them. I mean, here is the formula for the second case, and here is the formula for the first case. The only difference is that the FE exam has decided to use the concrete force, which is your compression force, and we are using the tension value, which is the same. Right? This one should be pretty much the same, very similar. Right? So here we use the tension side minus the effect of the flange, and here is the other effect again. But they tried to write the formula in terms of the concrete rather than the steel. Okay? And the way we have it is on the here is based on the steel. This one, because your moment is taken because of these two compression forces, normally the formula comes out as a formula based on compression values, and that's what it looks like this, right? And that's the reason why I guess the FE exam decided to put also this one in terms of compression, because the second formula is a function of the compression forces. Because the equilibrium is that T equals these two forces, where the two forces have a different D value, or a different arm, excuse me, and therefore that would not work if we use just steel. Okay, so design formulas then for this case, right? For this is the case here again. I didn't put this one before. This is the case where you have the flange is in tension, right? And this value, I forgot to put it here. Actually, I should put it also here, okay? Because that value is limited to less or equal than 80,000. So we should have those values limited also here. So if we do that, so that will be so we have then Fy less or equal than 80,000. All right, so that's what the limitation is on those formulas. I haven't mentioned that before, and I think we need to put them in because if we start using those 100s, the formula doesn't quite apply there. On there. So that's the 80,000, 80,000, 80,000, and the same for this one, right? So that would be the same. You had to use the 80,000. So we use the 80,000 there. Okay, so now you know. So that formula is limited then to steels up to 80,000. There is no really a formula that applies for 100,000. You would have to do your own, meaning that you had to check your cracking moment, which we haven't done. I mean, we have used 100,000, but we still have used the same formula. At this point, I think it gives you about close. I mean, very close. So it still can be used, but the code doesn't want you to use it. All right, the other thing that we had to do is, remember we said you're going to put rebars on the flange. Then the code says, well, you can spread these bars in the flange. But it varies, okay? If your B sub F is less than 1/10 of your clear span length of your beam, then you can put your bars on the flange. You can spread it out. If your B sub F is greater or equal than the 1/10, well, here much the same. So it's really greater than 1/10 of L sub n, then you will put your bars in a distance equal to 1/10 L sub n, and you will add extra bars on the remaining part of your flange. So I'm going to change this one. Let me see. Because it cannot be both, right? All right. So then you'll do that. Good. And this one right here is, remember I mentioned that on the beams, right, you go back to this figure that we have here, right? I mean, we're doing the design of these right here, right? And when you do your slab, you design this way, and you're putting bars here on the top, but you're not putting any bars on the top of these beams due to the slab. Okay? And that's the portion that your code says, well, yeah, you need to put something there because that is not bending exactly as a one way, and you need to add some reinforcement. And that's what this requirement is. Okay? So really what it is you're adding on those beams that are there, right? You're adding these bars there. In most cases, your temperature bars, which go in that direction, may fulfill that requirement. But you may want to check that, because you want to put those extra bars in there. Notice that these bars are not coming out of the paper, so these are not your main bars. These are bars transverse to your beam. They need to be calibrated. So you take this one, you design it like a cantilever section, and you come out with these values. That's what you do. Okay, so now we're going to do the actual slab and T-beam floor system, which is what you have in your project, right? The analysis is done by using the simplified method. We already went through that. There's the coefficients, remember, we've done that, right? And you had something different, but it's very similar, where you had these 114, 116, and 111 for your positive moments, right? And then you have these negative values that you will use for your negative moments, right? And finally, you got your shears, right? So shear coefficient. So these are the same coefficient method. You've already been using it. So let's look at that. So this is what it looks in your project. You will be designing this. Basically, you will be designing your slab like this. This is your exterior beam. These are probably your two exterior beams. This may be your other frame beam, right? And you're going to design that. So this is your project design for your slab. So we have the T-beam here, carries a nominal live load of 75 pounds per square footage, the load 110. Notice that I keep everything in PSF, right? The load includes the weight of the slab, 110 already, so yeah, could be. Partitions and utilities, so this is all your total day load. The T-beams are simply supported. I highlighted these because, I mean, every time you will use, when you come to the beam, you will use WL squared over 8 because you're trying to follow this example. Well, your beams in your project are not simply supported. So the beam cannot have a WL squared over 8. Okay? So your beams have to use these coefficients too. Okay? Same thing. So you cannot use the WL squared over 8. Okay. All right. So we're going to size our slab. We have different spans. In your case, you have only one span, so it would be easier. But here I have different spans. And so length of slab, 16 divided by 28. That's both end continuous. This one right here is one end continuous, so 1 over 14. So that gives me 685 and 7 controls. So my value is 7. I put here a note that you need to check for shear. Remember, because it's slabs, we don't put shear, so we want to make sure that we carry the shear by the concrete, right? The beam, in this case, is simply supported, so I can use L over 16, so it's 26 divided by that. And because this is your minimum, because I'm designing, I'm going to add 20%, I'm going to make that 24. Okay? So 24 is that. In terms of the width of my beam, I can use 12 inches. But in this case, I want to use 14 to have enough space. Right? Also, you have to be careful here because you have columns that are going to be probably 16 by 16, right? You want your width of the beam to be equal to your column width. And so that means your beams are going to be 16, all right? All right, factor loads. I got the two combinations, the 1.4D and then the 1.2 and 1.6. That one controls. So now I have a load of 252 pounds per square footage. That's the total load on this floor, factored. Okay. For my slab, I'm going to multiply that times 1 foot, remember, and that becomes now 252 pounds per foot. Okay. And then I'm going to use my coefficients, and I'm going to plot my moments. So this is what we were plotting when you said plot your envelopes. Remember that you had to do that in your project, right? So right in here, that's what you need to do. So these are your values. You're finding all these numbers. All right, so we apply the coefficients. This is the negative moment on the end, right? So we are looking at the negative moment at the end, right? So it's 124 because we are going into a beam. If we go into a column or we go into a wall, you have to use 1/16, okay? But 124 for us. The first interior 1/10, and the next values are 1/11. Okay. So we come in here then, so there's that one. The other negative value 110, the other negative value 111. Okay. Now the spans here, this span is different, right? Why? Because for negative moments, so only for negative moment coefficients, ln average of the two adjacent spans if the spans have different lengths. Only for negative moments. There is nothing of that in the positive moments. Okay? But your negative moments have that. So in our case, right, the span lengths here we got 14 and 16. So when we do these moments here, right, which is the 1/10, the 1/11, I have to use the average. And so here is the average with the 1/10, right? Average of the lengths, and I got that. The average for the 1/11, and I got that one. Right? When I have to do the negative moment here, right, or here, I don't have average length because these two are the same. So I'm going to use the 1483. So that gives me a different value there, because that is this one. Okay. Now my positives. I got two positives, right? This one and that one. So those are the 114 and the 116. Okay. This one we don't use because that is for simply supported support. Right? Okay. So we got then those two positives, and this is my first positive, 14, and the other positive, 16. Okay. All right. So what am I going to design for? Well, basically I got a 504 here, negative, right? Which covers this guy and covers this other guy, so covers these two, so I don't have to worry about those. I'm going to design for that one. There is a 346 positive that covers the 296, so I'm going to design for the 346. Now there is a negative that is pretty low, 173, so I probably need to check that one. Okay, so that's the very negative here. So I have then three moments that I have to check. My H is 7, my B is 12, of course. I'm going to assume number 4 bars. That gives me my D and D sub T value. My M sub N, find my area of steel, right? So once I got my required area, I select the bar. This is pretty close to 0.20, so I'm going to say 0.20 is going to give me a value larger than 12, right? But we don't want that, so we're going to say use 12. So number 4 is at 12. Okay. And since that's number 4 is at 12, that means that my provided area is 0.20 at 12, right? So I don't have to find the provided because it's exactly 0.20 at 12. The minimum value, we check it, and we satisfy minimum, right? The spacing is 18, we got 12, so we're good. Right? Yeah, that one. Okay. So number 4 is at 12 work. I'm going to verify my phi factor. So I got my D sub t here. My A is provided, as I said, is 0.20 per foot. I mean, there is no change really there. Find my A value, find my C over D sub t, very good. So I satisfy my A is maximum. I have a phi factor of 0.9. And then I go here and check my capacity, and my capacity is good. So number 4s at 12 for the negative moments are good. Now, then it comes the really small moment that I have, the 173, right? But on that one, since we are using already number 4 by 12, and this is the practical minimum that we can use, then we will use the same value for that one. Mm-hmm. We cannot go really lower than that. Let me add here something. AS max, right? So A maximum is satisfying. All right, so we got it. Okay, now we're going to do the bottom reinforcement. The bottom reinforcement, I can use number 3 bars if I want to, because it's in the bottom. All right. Bottom reinforcement moments, remember, is the 346. Right? Do I have to design it? Well, I'm going to design it just to show you that. But really, that means you found already number 4s at 12 for 5. So I will use the same here too. And I have all this lab, positive and negative, number 4s at 12. That will be a very nice design because there is no confusion, right? Number 4s at 12 in the bottom, number 4s at 12 in the top. Right? Very good. But just for purpose of illustrate the number 3s, I'm going to do that here. So I'm going to try number 3 bars. I'm going to do the same, find my D value, find my A value. I got a value here at 0.13, but this is below the minimum, so I had to use the minimum. If I use the minimum and still keep my number 3s, then I have to put a spacing at 8 inches. Okay. If I use my number 4s, right, I get an S of 16 inches, okay, which is below the 18 inches, right? Which apparently looks good, right? It looks good. I'm doing my 0.20 at 16, so I'm providing exactly the minimum. I'm good. Check again my capacity, my phi factor, my ductility, and my AS maximum that I just put in here. Right, so this one is satisfied. So we have that one here. So it is satisfied. So the design then capacity, pretty good. Number 4 is at 16. Okay? You say, oh wow, I think number 4 is at 16. That's great. Okay? But now it comes cracking control, right? So negative values, we have number 4 is at 12. They're put on the top, right? And positive values are number 4s at 16 at the bottom. Okay. Check cracking control, put the formulas, 60,000. What is the controlling value? 12. Oh. So for the top mat, right, for the top mat, I'm okay because I'm doing number 4s at 12. But for the bottom mat, right, I cannot use the 16 inches. Right? For cracking control, I had to use 12 inches. So I had to change the 16 back to 12. So everything becomes now number 4s at 12. Okay. My temperature and shrinkage goes by the minimum. And again, here I can use the 16s. So I can say number 4s at 16s, okay, for temperature reinforcement. So top mat, number 4s at 12. Bottom mat, number 4s at 12. And temperature, number 4s, 16. Inches. And so when it looks here, you have these are your main bars in the direction of this lap, right? So these are your main bars. Well, direction of this lap, main bars. These are your direction of this lap, main bars. Positive bars, negative bars. So number 4 is at 12. Remember, your temperature goes in the inside, right? So it goes in the inside, and his number 4 is at 16. and you have finished the design of your slab. Pretty quick. Shouldn't take you very long. Okay, so let me stop here, and then we're doing another video. We'll do the T-beam design.